you guys, we are going to do just an intro to acid-base equilibria. So this was one of the units that got cut from the AP test, but there could possibly be some questions that refer to like the acid or the base. So it's important to understand what those are in a problem or in an equation. So first, some properties. Acids tend to taste sour. They cause certain dyes to change color, so you could do some sort of pH test on them. And acids, this is kind of the key thing, they always contain a hydrogen. And specifically, it's a hydrogen that can be ionized. So it's not a hydrogen in the middle of an equation, it's a hydrogen on either side that can be taken off. Bases have a bitter taste, they feel slippery, and some bases have a hydroxide ion in them. So there are two different models of acids. So the kind of most basic one is Arrhenius model, and he basically said an acidic substance is one that when you dissolve it in water, it increases the concentration of hydrogen ions. So something like HCl, when dissolved in water, breaks into the H plus ion and the Cl minus ion. So when it dissociates, if there's a hydrogen ion that dissociates, Arrhenius would say that it's an acid. Following that definition, a base is a substance that when dissolved in water increases the concentration of the hydroxide ions. And hydroxide is the OH minus ion. So something like sodium hydroxide breaks into sodium ion and the hydroxide ion. So Arrhenius's model of the acid is very good, but its base is really limited. So Arrhenius only calls things that have the hydroxide ion a base. And we know from experience, or scientists know from experience in the lab, that bases don't always have hydroxide ions. So just like any theory in science, when we prove it wrong or find faults, we keep working on it. So the next model of the acids is the Bronsted-Lowry model. So Bronsted-Lowry based his model of acids and bases on the transfer of hydrogen ions. So instead of doing the hydrogen and the hydroxide, he is focusing just on the hydrogen piece of it. And that hydrogen ion can either look like this, an H+, or it can be H3O+, which is hydronium. And hydronium comes from being in aqueous solution, so water, and adding a hydrogen ion to it, and those things combine to form the hydronium. So when we have hydronium, we're talking about that extra hydrogen ion that's combined with water. Sometimes that's shown in an equation, and sometimes it's just written as the H+. They're both okay notation for an acid. So because we're focusing just on hydrogen for the Bronsted-Lowry model, we have to explain what an acid does with the hydrogen and what a base does with the hydrogen. So in the Bronsted-Lowry model, acid is a proton donor. So it starts with a hydrogen at the beginning of the reaction and it gives it away, so it no longer has it at the end. A base is a proton acceptor. So we can tell that it was a base because it will start one way and then it will end with another hydrogen attached to it. So if Bronsted-Lowry acids are donors, that means they must have a removable proton. So there must be a hydrogen, and they usually come at the beginning for acids, that can be taken off and given to the base. The base must have a pair of non-bonding electrons. That means they have to have a place where a hydrogen that's donated can come in and be given to it. Okay, so look at some examples of this. One other thing. There are some substances that can act as an acid or a base. These are called amphiprotic. So we're going to be talking about protons here. And when we talk about protons, we're talking about the hydrogen which is positive, is our proton. And so amphi means that it can be both. Like if you're ambidextrous, you can use both hands. Amphiprotic means that it can give away a hydrogen, so it has a hydrogen to give. But each of these also have an extra set of non-bonding electrons that could accept a hydrogen as well. Okay, so acidic reactions are always done in a solution of water. So water acts as the Bronsted-Lowry base and accepts a proton from the acid. As a result, we get something called a conjugate base and a conjugate acid. So in each of these scenarios, we're going to identify the acid and base on the reactant side, the left side. And then once the hydrogen has moved, we're going to identify something called a conjugate acid and a conjugate base. So we're going to make acid-base pairs. So here our acid donates the hydrogen. So on the product side, it no longer has a hydrogen. So now we're going to call it the conjugate base. We're going to call it the CB. The base, which is our water, we can see that it's a base because it starts with 2 hydrogen. And now over here, it has 3 hydrogen. If it's a base on the reactant side, now it has an extra hydrogen. It becomes the conjugate acid on the product side. So we can see in this, conjugate comes from the term conjugare, meaning to join together, or like when you conjugate verbs. So reactions between acids and bases always yield with conjugate acid and base pairs because we're moving that hydrogen or we're bringing it together with something else. So if it's an acid on one side, that hydrogen that's there on the reactant side is no longer there on the product side, and so it becomes the conjugate base. The base, we can see, because on the reactant side it only had 2 hydrogen, and on the product side now it has 3. So the base accepts a hydrogen, becomes a conjugate acid. Okay, so let's look at this again. So we are going to follow the non-hydrogen things, okay? So we're going to follow the nitrogen, over to the nitrogen here, and we're going to look at what happened. So on this side, there are 3 hydrogen, and on the product side, there are 4 hydrogen. So it gained a hydrogen, which means that it's a base. So on the reactant side, it's a base, and once it gets that extra hydrogen, it becomes a conjugate acid. Okay, so that means that the other thing, and we'll double check, but the other thing should be the acid. So in this case, water is acting as an acid. So it started with 2 hydrogen, and now it only has 1. So it's losing a hydrogen ion. So it was an acid, and it's become a conjugate base. So again, we're connecting together the non-hydrogen things, our nitrogen and our oxygen, to see what our pairs are. But then we have to follow the hydrogen to see if it's the acid or the base. Okay, so let's do this again. So I've got my H2S, and I'm combining it with my other S substance. So I have 2 hydrogen in my reactants and only 1 in my product. So I lost a hydrogen, which means that it's an acid in the reactants, and then it's its conjugate base pair. So we'll double check, but the other one should be a base. So I'm starting with 2, ending with 3. So I have a base, and it accepts a hydrogen and becomes conjugate acid. So one last thing, not all acids and bases are created equal. So you can have strong acids and strong bases, and this is based on, so the strength is based off of how much it dissociates or breaks apart in water. So strong acids are going to be things that completely dissociate in water. So they completely lose that hydrogen and become conjugate bases that are quite weak. So the stronger the acid, the weaker base it makes. Weak acids only partially dissociate in water, meaning that there is some of the acid left and some of the conjugate base. Weak acids are going to be part of an equilibrium with the double arrows, because we're going to have some of the acid left and some of the conjugate base made, and it'll kind of create a balance there. You can identify strong bases and weak bases in the same way, looking at how much they dissociate. Okay, so here's a scale. Substances with negligible acidity do not dissociate in water. So things down here, like a hydroxide ion, which is like the definition of a base, is not going to be acidic at all. But what that tells me is that its conjugate base is very strong. So the stronger the acid, the weaker its conjugate base. The weaker the acid, the stronger its conjugate base. So we can see that hydroxide conjugate base is a very strong base. So if it were to lose that hydrogen, it becomes a very strong base. Okay, so you guys, that is kind of the general acid base. Again, this is more so that if they refer to the acid or to the base in a problem on your AP test, that you are able to identify that in the problem. Let me know if you have any questions. Otherwise, if you take another chemistry class, you will go into much more detail about acids and bases.